All right, well, good afternoon, everybody. Welcome, good to see you, and welcome to our viewers on video as well. Okay, so today we're going to look at some additional issues around the problem of synchronizing threaded programs. First, though, let's review from last time a few of the concepts. So recall that a semaphore is a non-negative global synchronization variable. It's manipulated by P and V operations. And the P operation takes as an argument a semaphore. If the semaphore value is non-zero, it decrements the semaphore and then continues. If the semaphore value is 0, then it blocks, waiting for that semaphore value to be incremented by a V operation. After the V operation increments, after some V operation increments the semaphore, the P operation continues by decrementing S and then returning control to the caller. The V operation never blocks. First it increments the semaphore value S, and then it looks in the queue to see if there's any processes that are blocked, waiting for that semaphore to be non-zero. If there are, then it selects one of those using some unspecified criteria, and then it restarts that thread or that P operation that's waiting on the semaphore. Okay, and then the semantics of the P and V ensure that semaphore values are always greater than or equal to 0. Now, the first thing, we saw how to protect shared variables by using a semaphore called a mutex that guarantees mutually exclusive access to the critical sections that are updating those variables or data structures. And the way that we do this is very simple. We initialize the mutex to 1 and then surround the critical section with a P and a V. Now there's other ways that we can, so here's an example where we're using semaphores to provide mutual exclusion. But we can also use semaphores to coordinate access to shared data structures in different ways. And so the idea here, before we were using the semaphore just to protect the access to a shared variable, but we can also coordinate access in different ways by in these kind of scenarios, we're using the semaphore to keep track of state, to count things, to keep track of state, and to notify other threads of changes in state. Okay, so it's a very different usage model. And two classic examples that we're going to look at are the producer-consumer problem and the readers-writers problem. So let's look at producer-consumer first. So the idea in the producer-consumer problem is that you have a shared resource in the form of a buffer. The buffer has a bounded size, so it consists of n slots, and each slot can hold an item. Okay. There's a producer thread which produces items and then inserts them into the buffer. And there's a consumer thread that removes items from the buffer and then consumes them by acting on them in some way, processing on them in some way. So the synchronization variable, the synchronization pattern is that the producer waits for an empty slot, right? So if the buffer's full, the producer can't insert an item into the buffer. So it waits for an empty slot, and then when it finds an empty slot, when an empty slot becomes available, it inserts the item into the buffer, and then it notifies the consumer that there's now a new item in the buffer. The consumer, of course, has to wait for an item to show up in the buffer, right? Otherwise, I mean, it can't remove an item from an empty buffer, so it has to wait for an item to be available in the buffer, and when an item becomes available, it removes it from the buffer, and then notifies the producer that there's now an available slot. Okay. So this very simple pattern is actually really, really useful and shows up in a lot of applications. So for example, a multimedia application. In a multimedia application, the producer might be producing, say, MPEG frames in a video, and a consumer would be consuming those MPEG frames and then painting the screen appropriately. Another important application is in graphical user interfaces. So graphical user interfaces are typically implemented using this producer-consumer model, where the mouse clicks, motions of the mouse, keyboard clicks, those are all recorded as events. They're detected by the system, recorded as events, and placed into some kind of a queue. And then various other parts of the system retrieve items from the queue and react to them. So for example, the graphics system will retrieve events like mouse events and mouse movements, mouse clicks, and it'll paint the screen accordingly, right? So it'll reflect, it'll repaint the screen so that to show you that the cursor's moving, right? Or if you change the focus, it'll repaint that. So it's a very very common model, and as we'll see later, we can build multi-threaded concurrent servers using this model. Okay. So let's see how we would implement producer-consumer on an n-element buffer. So the implementation requires a mutex to guarantee mutually exclusive access to the resource, of course, and then it requires two other semaphores, counting semaphores. Slots is a semaphore that counts the available slots in the buffer, and items counts the available items. Okay, and we can implement it with this package called sbuff. So sbuff, the sbuff package defines a type called sbuff_t that packages up all of the data structures that are needed to implement the shared buffer. So there's a pointer to the buffer, which we were going to implement as an array, and we'll implement a circular buffer on this array. The maximum number of slots, n, so the size of the buffer, and then two pointers, front and rear, to keep track of the front and rear of the buffer, so to keep track of the first and last items in the buffer. And then the three semaphores, the mutex and the two counting semaphores. And then the package consists of these four public functions, sbuff init, which is called once to create the buffer and initialize everything, allocate the space and initialize things, and then dinit, which frees up the space, and then a function to insert an item into the queue, and a function to remove an item from a queue and return that item. So in this case, items are just ints. Okay. So to create to initialize this buffer with n slots, we first allocate the space for the buffer n ints. We set the size to be the value n that was passed in. We indicate the empty buffer by setting front and rear to be 0. Okay, and so whenever front and rear are 0, we have an empty buffer. And then we initialize the three semaphores. So the mutex, like all mutexes, is initialized to 1. The slots semaphore, which keeps track of the number of available slots, is initialized to n. And the item semaphore is initialized to 0. Okay. And dinit is really simple. It just frees up the heap space that we allocated. Okay, so now let's look at how we insert an item into the buffer. So we want to insert this integer item into this buffer pointed at by SP. So first, the thread waits for an available slot, okay, by doing a P on the slot semaphore, right? So P will block until slots is greater than or equal to 1. Okay, once there's an available slot, then it's going to update the rear of the buffer. Okay, so we're going to put this item onto the rear of the buffer, and so it needs to protect that access to that shared buffer with a mutex. Then it does by doing a P on the mutex, updating our rear pointer. Okay, so we pre-increment it. So we increment the rear pointer and then take the mod of that n to compute the index that we're going to insert the item into. Okay, then we do a V on the mutex. Okay, so that other threads can update that shared data structure, and then we do a V on the number of items to notify any consumers that there's now an item in the buffer. Okay. So this V is kind of interesting. You can think of it as kind of like a signal, right? So you're sort of signaling consumers that now some event has occurred in the system. Now to remove an item, it's symmetric, but instead of operating on the slot semaphore, it operates on the item semaphore. So to remove an item, a consumer first does a P on the items semaphore. So this now is waiting for an available item. It's waiting for the semaphore to be greater than or equal to 1. When that happens, then the P returns, and then we do the update protected by a mutex by pre-incrementing front, taking the mod n, and then reading that value and returning it and placing it into this local variable item. Then we release the mutex, and then we do a V on the number of slots, which is an announcement to any producers that there's now a new available slot. Okay. Is there any questions about that? So it's a little more subtle. This looks really simple, but like all concurrency problems, it's actually very subtle. So you can have potentially many producers and many consumers all operating on the same shared buffer. So what would happen if we had two consumers did a P on this item semaphore at the exact same time? Say we're running on 2 cores, and we have 2 threads, and they each execute that P at the same time on that same item semaphore. Okay, so even though they access it at the same time, the kernel will make sure that one of them will execute first. Okay, so the kernel will serialize those P operations. And there's no telling which one gets it first, but whoever runs their P first will decrement this item semaphore, and then when the next thread executes its P, items will either be 0 or non-zero. Okay, as a result, so somebody wins. It's kind of like a controlled race, and somebody wins the race, always wins the race, because the kernel is serializing these P operations and it's executing them atomically. Okay. Okay. Now there's a generalization of the mutual exclusion problem called the reader-writer problem. So with the mutual exclusion problem, we were guaranteeing each thread mutually exclusive access to its critical section that's updating a particular resource or accessing a particular resource. And we did this the exact same way whether that access was a read or a write. Okay. But that's overly conservative in this case, because we could, if all we were doing, if we had multiple threads that were just reading the resource, there would be no reason to do P's and V's on that resource. Right? If we're not changing the resource, if we're just reading it and there's nobody else writing it, then there's no need to protect, right? So for readers, we can have as many readers as we want, all at the same time reading the resource, the variable, or set of variables. And there's no need for any kind of synchronization at all. Okay. So the producer-consumer is sort of a generalization of that mutual exclusion problem, which enforces mutual exclusion only when it's absolutely necessary. Okay, so there can be as many readers reading the resource, but when a writer wants to write, then it has to have mutual exclusive access to the resource. Okay. So this is the kind of thing, this is also a very useful pattern. You have, in an online airline reservation system, you have multiple clients accessing a shared database. Okay, so as long as those clients are reading the database, they can all be reading at the same time, but as soon as somebody wants to make a reservation and update the database, then that update has to happen in a mutually exclusive way. You know, if you had like any kind of shared data structure, like a cache in a concurrent proxy, like that you're going to be writing soon, or if you haven't already started, that cache is being shared by multiple threads, and multiple threads may be reading that cache, but when you get a new page and you want to cache it, then that constitutes a write, and that write needs to happen in a mutually exclusive way. Now the initial research, the researchers that pose this readers-writers problems define sort of several classes of reader-writer problems. The first readers-writers problems is an implementation that favors readers, right? So the idea is that no reader should be kept waiting, right? Unless a writer already has has sort of acquired the lock on that, or the mutex on that resource. So in this case, you know, say there's a writer waiting to acquire the mutex, and another reader comes in, then in this implementation, that reader would get priority over the writer, and it would be able to read to do its read, and the writer would have to wait. And so, of course, now if multiple readers keep coming in, then this could starve out the writer, right? So a writer could be starved sort of indefinitely, waiting for all these readers to finish. And it's just based on, you know, based on how the operating system decides to schedule these various reader threads. The writer could be starved out. So that's what we mean by when we say that it favors readers. Now the second readers-writers problem is sort of the opposite of that. So it favors writers, right? So once a writer is ready to write, then it gets priority over any waiting readers. So in this case, if we have multiple writers that want to write, they could starve out readers, right? And now there's other variants that sort of deal with this starvation issue, this potential starvation issue, but we won't look at them here. So let's look at the solution to the first readers-writers problem. So initially, a thread is either a reader in this sort of simplification, or it's a writer. If we look at the writers, this is pretty simple. It's just the writers are just doing a P on this semaphore. So this semaphore W is sort of serves as like a mutex that protects the resource for writers. So it ensures that there's at most one writer at any time executing its critical section, and it does that by just this familiar P followed by a V. Okay, now readers are a little more interesting. So with the reader, we have this shared this global variable called read count, which is going to keep track of the number of readers that are waiting to read the resource. And there's a mutex, semaphore mutex, that protects the accesses, the updates to read count, okay, the reads and the writes to read count. And then there's this W semaphore, which, as we saw here, is used to protect the critical section in the writer. And initially, both of these are set to 1. So the reader in this infinite loop, in each iteration of this infinite loop, it is going to increment read count. So it protects that access by doing a P on the mutex, which is associated with read count. So only one reader can be, so this region between the P and the V constitutes the critical section corresponding to read count. So after the P completes, then we increment the read count. So now there's an additional reader. Right? So we can have potentially an arbitrary number of these reader threads. Right? So we're indicating that there's a new reader now. And if read count is 1, that means we're the first reader. Okay, so this is sort of the first reader into this implicit queue of waiting readers. So if read count is 1, if we're the first reader, then we do a P on W, okay, which now will lock out any future writers. Now, if there's already a writer that's done its P of W, then this will block, waiting for that writer to finish. Okay. But if there's no writer inside of its critical section, then this P will just decrement the semaphore W from 1 to 0, and then lock out any subsequent writers. Okay, so now after it's done this increment and read of the read count variable, then it releases the mutex so that other readers can access read count. Okay, now, but it's still holding. It's holding. So this is kind of interesting, right? It's holding this semaphore that locks out the writers, but it's not holding any mutex, right? So the reader now can just read. It can do its read, and other readers that are in the same section of the code can also do their reads, right? So we're not. So we're allowing multiple readers now inside this critical section, but no writers. Okay, so everything looks like it works good. Now after we read, now the number of readers now is going to be, we want to decrement the number of readers. So we acquire the mutex on read count, we decrement read count, and then we check to see if we're the last reader. Okay, so if there's no more readers, in other words, if read count is 0, then now we can release the mutex for the writer, so that now writers can access that resource. And after we release that, the writer's mutex, then we release the mutex for read count. So any questions about this? So an interesting for you to think about, just if you have any spare time, is how you might write a version of this readers-writers problem that favors writers instead of readers. Okay.
So I have a question.
Yes.
So just to be clear, so mutex allows for multiple readers, but
Oh no. Okay, so the question is, a mutex allows for multiple readers. The fact that we're releasing this mutex here, this mutex is only protecting access to read count. So we acquire it here and we release it here after we've accessed read count. Okay, but we're not protecting the critical section of the reader with any mutex, except for we're keeping writers out by, if we're the first one in, if we're the first reader, you can imagine there's like this implicit queue of readers that we're keeping track of with read count. Okay, so if we're the first ones in, meaning we're the first reader, then we acquire the P on the writer's mutex. Now, of course, if there's a writer inside this critical section, then this P will wait until the writer releases. Okay, but once we've acquired this mutex W, then we're locking out any writers. Okay, because any writer that arrives will do a P and it'll block right here on waiting for that W to be non-zero. Okay, so we're blocking out any writers, but then we're allowing any readers to just to access the resource. Okay. Okay, good. Yes, question.
Is blocking slow?
Question, is blocking slow? It can be, depends. Well, first of all, you're making a call into the kernel, so it's a system call. So you're crossing that boundary, and there's always overhead associated with that. And then blocking, you're blocked until, it can be sort of an arbitrary amount of time, right, until some thread does a V. So yeah, it can be slow, right? It just depends. You can't, it's really hard to bound the time that you're going to be blocked. Now, if you write the program correctly, eventually you'll be unblocked. Eventually some thread will execute a V. But when we're sort of assuming that the kernel does some kind of, when it implements its V, it does some kind of fair scheduling so a blocked P won't be in its queue forever, right? That the kernel does something that's fair, so it guarantees that a P won't remain blocked indefinitely. Okay. Any other questions? Okay, so we can kind of put all of this together and use our producer-consumer model to implement a pre-threaded concurrent echo server. Now, so far when we've used threads in all our examples of using threads and processes for servers, we created a new thread or process whenever a new connection request arrived, and then that thread interacted with the client, and then whenever that interaction was finished, it closed the connection and exited and killed the thread or process. Now that's okay, but it's inefficient, right? Because this creating and killing threads introduces overhead. So another way to do this is to create the threads or processes ahead of time, create a pool of threads where each thread, so we create a pool of these worker threads where each of these worker threads can interact with a client. Okay. So instead of sort of creating processes and threads on demand, we create what we call a set of pre-threaded or pre-threaded threads or pre-forked processes that do the work. So the idea is that we have this master thread in our server that's waiting for connection requests from clients by repeated calls to accept. And then when this thread receives a connection request from the client, the accept function returns a connected file descriptor, okay, associated with the connection to the client, and then it inserts that descriptor into a buffer. Okay, now remember, descriptors are just small integers that index the descriptor table, right? So they can be passed around from thread to thread because all the threads are sharing the same descriptor table, right? So the master thread puts repeatedly accepts connection requests and inserts the corresponding connected file descriptor into the buffer. Now, each worker thread waits for so in this case, the items are descriptors. So the worker threads, they're all waiting on this for items to appear in this buffer. Okay. And when an item appears, one of the threads will remove that item. and then use that descriptor to interact with the client over the connected file descriptor associated with the connection that exists between the client and the server. Okay, so now we have these, the concurrency comes in the form of these multiple worker threads interacting with multiple clients. And then when a worker thread finishes servicing a particular client, then it just goes and it checks for the next file descriptor in the buffer. Okay? So this is much more efficient than our previous model, where for each new client we had to create a thread or a process and then destroy that thread or process once we were finished. Okay, so we're sort of amortizing all the work that we had to go through to create these worker threads by leaving them running and then replacing the destruction or the killing of that thread with replacing it with just a simple and very fast operation of removing an item from the buffer. Okay. Okay, so let's see how we would implement this. And like all of these server examples, it's surprisingly simple, right? This is a fully functioning, a real server, but we can do it in one page of code. So for this we're going to use threads for our concurrent server, and we're going to use the sbuff package. So we're going to create this shared buffer, global variable called sbuff. And we have listening descriptor and connected descriptor, and we have the client length and client adder that'll be used in the accept call, and we have the thread ID that'll be used in the when we create this thread. So now we start by in this program we're going to pass in the port number. So this server is going to be listening on some port. So we pass that port number in as the first argument. So we call open listenFD on argv of 1. And open listenFD creates a listening descriptor and returns the value of that descriptor in listenFD. And then we call sbuff init to initialize our shared buffer with sbuff size file descriptors. And then we create a collection of nthreads worker threads, each of which will execute the thread routine, which we've called thread, and no argument. So once we create all of these threads, then we go in this infinite loop where we call accept on this listening descriptor. So then accept will block until a connection request arrives. And when it does, the accept returns with a connected file descriptor that can be used to interact with the client. And once we get that connected file descriptor, then we just simply insert it. We insert that connected file descriptor into our shared buffer and then wait for the connection request, the next connection request. So our server's very efficient, right? We're just doing an accept and then a very fast insert into the buffer. Okay, and then we're going to let the worker threads do all the work associated with that queue of descriptors. Now the thread routine first detaches. Okay, so this is a case where we don't want to run joinable because we're never going to join. We're never going to wait for these threads or have any reason to kill them from the main thread. So now this worker thread in this infinite loop, each iteration, it removes an item from the buffer. So it blocks until there's an item that it can remove from the buffer, and it sets it to this local variable confd. And then it calls a helper, sort of this is like the helper function that implements the logic for this particular server. And in this case, it's an echo server. So this echo count routine will interact with the client, echoing whatever the client sends us until the client closes the connection. And then whenever the client is finished, then Then we close the our end of the connection and go back and get the next item out of the buffer. And I should point out that echo count is just a placeholder. This could be anything. This could be the logic for a web server or for any kind of web service or any kind of service. Now, to initialize this echo count function, we need to initialize the mutex. So this echo count function is going to have it defines a global variable called byte count. So in this echo server, we're going to keep track of the number of bytes that we've received from all the clients that we're interacting with. Okay, so there's a global variable called byte count, which is shared by all the threads, and we're going to update this byte count variable every time we receive every time we receive data from the client, and we're going to use mutex to protect the accesses to byte count. Okay, so we're going to have to call a function that initializes this by first initializing the mutex and then setting byte count to 0. And then within echo count itself, we've already seen a way to initialize a package. You know, if we have some kind of package of library functions that are going to be used by multiple threads, there's several ways to actually initialize this package. So one way is to explicitly have the main thread call this initialization function once. Okay, so we've seen that with like the sbuff package, right? The main thread has to calls sbuff init once, okay, before any of the peer threads execute, any of the worker threads execute. But there's another way we can do this too. We can have the worker threads actually call the initialization function, and we can use this technique provided by pthreads, where we define a static variable. So this is a static local variable, but you recall that this is actually treated like a global variable. So every thread has access to this variable, okay, but its scope is limited to the echo count function. So no other function can access this variable, but each thread that executes this thread routine has access to it, and in this context, it's treated like a global, right? So if one thread updates the value, every thread sees that same value. Okay, so we can use this mechanism from pthreads so we can create this variable of type pthread once t and initialize it to this special pthreads value, which is sort of like the pthreads uninitialized value. So this is a value that pthreads knows about that indicates that this variable once hasn't been initialized. And then we call the pthread once function, passing it this variable that the address of this variable that we created, and the address of the function to call to initialize whatever it is we want to initialize. In this case, the echo count, the echo count variable. And so what this does, every thread will call pthread once, but only one thread will actually call the initialization function. Only the very first thread that executes pthread once will call it. The other threads, this pthread once call will be like a no-op. Yes, question?
If you're just initializing this once, why don't you just do it like once in the master?
Well, that's the other option. So the advantage of this is that you can I guess the advantage is, I don't know, it's just another way you can do it. I guess it avoids having to do it in the master thread, that you can make this package sort of self-contained, right? That you're not really counting on the master doing anything. But yeah, that's the other way we could have done it. So I just wanted to show you this other technique. Okay, so once we initialize, once some thread calls a init echo count, then we initialize the Rio package for all of our accesses on this connected descriptor. And then we repeatedly read a line of text from the client. Okay. And then in a protected way, we increment byte count with the number of bytes that we received from the client, which is returned by this Rio readline B function. And then we print a little message just to sort of keep track, so we can see, keep track of our running total. And then we release the mutex on the byte count, the global byte count variable, and then we echo that line back to the client. Okay. So any questions about that? Yes, question?
Just to confirm about like the static variables. So the line that declares it will only get executed the first time that line is declared?
Okay, the question is, the line that declares the static variable once, will it only be executed the first time a thread executes that statement? No, so the answer is no. Every thread will define this variable and assign it to this pthread once value. Okay, what will only happen once is the call to init echo count. Okay, so the first thread that executes this pthread once call will actually call init echo count. Every other thread, every subsequent thread, will not call it. It'll be like a no-op. So,
does it use the once as a flag?
yeah, it uses the once. It's just an opaque.
But then when the other function calls the declaration line, won't it be resetting the flag by resetting its pthread once init?
Yeah, somehow it will, but somehow the pthread once is keeping track that it's executed. Okay, so I'm really not sure how it's implemented. Okay, so somehow pthread once. Yeah, I guess this. I mean, this is just a C declaration, right? So the pthreads has no control over declarations, right? So every thread will sort of update this static variable. And you're right, if the first thread, the second thread would overwrite this value again. But somehow pthread once keeps track of that, okay, in some way that I'm not sure about how that works. But this is the way you get that behavior. Okay, now there's some other issues around synchronizing threads, sort of correctness issues that we have to be aware of. And so I hope you're sort of getting the sense that this threaded programming is kind of a tricky business, right? And so one issue that we always have to be aware of is this idea called thread safety. So in general, a thread routine should only call functions that are thread safe, that have this property called thread safety. Okay, and a function is thread safe if and only if that function can be invoked by multiple threads at the same time. Okay, so if we have a function f, it's thread safe if and only if its execution can be interleaved by multiple threads. Okay. And so we can identify 4 different classes of thread unsafe functions. So one class is the functions that fail to protect shared variables with mutexes. Okay, so we've already seen that with bad count. That was an example of a thread unsafe that main routine was an example of an unsafe thread function. Or no, the thread function was an example of an unsafe thread function because it didn't protect the update of the count variable. Another class of functions that are thread unsafe are those functions that keep track of state across multiple invocations. So if they're storing state in some global variable, private or public global variable, then that's thread unsafe because multiple threads will be accessing that state. Another kind of thread unsafe function are functions that return a pointer to a static variable. So there's a number of functions in the standard C library that were written before threads were even on anybody's radar. And so an example is the ctime function, which takes as an argument a time struct, a binary time struct, and returns a pointer to a string, a date and time string. But the address in that pointer is always the same, right? So this function is defining some kind of static variable, and it's always returning, and then it's converting the binary time struct into a string that's always at the same location, and it's returning the address of that string. So every invocation returns the exact same address, but with different content at that address. Okay, and this, they didn't realize that this was a bad thing to do for threaded programs because nobody was writing threaded programs at the time. And then obviously any function that calls a thread unsafe function is thread unsafe. Okay, so let's look at these different classes of functions. Okay, so the class 1 functions fail to protect shared variables. And so the fix, as we've seen, is to use P and V to guarantee mutually exclusive access and thereby protect the accesses to the variable. So we saw this with that good count program. And then the problem is, and also as we saw with good count, is that the synchronization operations can be slow. So if they're in a tight inner loop, it can really slow your program down. Okay, the class 2 thread unsafe functions rely on some kind of persistent state across invocations of that function. Okay, so the classic example is the libc rand function, an implementation of which is I took from the K&R book. So this rand, this is a pseudo-random number generator. It's pseudo-random in the sense that if you give it the same key, it'll return the same sequence of values. Okay, so this is kind of nice because it allows, when you're testing, it allows repeatability. So every time you call it, if you call it with the same seed, you're guaranteed you'll get the same results. And the way this is implemented is that there's the seed. There's a seed variable called next, which is used in each iteration of the random number generator, and it's defined as a global, private. So static makes it private, so it's not accessible to programs that are calling the rand function, but it's used by the rand function. And so this variable is initialized to 1. There's a function called srand, which allows the user to set the seed value. So the default seed value is 1, but if the user calls srand, they can pass in a seed, which is just assigned to this next variable. And then each iteration of rand does an operation on the seed. So it takes the next value that's going to be used is a property of the previous value, the function of the previous value. And then it returns a pseudo-random number that's a function of that next value. Okay, so it's relying on this, each iteration, each time you call rand, you're relying on this next value that was computed by the previous time that you called rand. Okay, now this is perfectly fine, and there's no problem with this in a non-threaded situation. But what happens if multiple threads now So suppose you have multiple threads, and they're each calling this rand function, sort of interleaving calls to rand. Okay, the fact that rand is relying on this previous state, if multiple threads are calling rand, it's going to break this pseudo-random property. So each thread, the random numbers that each thread gets back are not only a function of the seed from the previous time that thread called a function, but also a function of the other threads that are calling it, right? So if a particular thread calls this random number generator multiple times, it potentially won't see the same sequence of pseudo-random numbers because other threads will be jumping in, okay? So it's not incorrect in that the program will fail, but if the program is counting on the pseudo-random property, then it creates a problem, okay? So the solution to this is to rewrite rand and require the caller to keep track of this next variable. Okay, so each caller will keep its own local copy of next, and it'll pass in a pointer to rand. Rand will compute that value, so now this will be updating state in the calling thread, but this is local state on that thread stack. Okay, so every thread will have its own copy of next. So, but we have to create a new function, and we'll call it underscore R. This stands for reentrant, which is a property we'll look at in just a second. But it's more work for the programmer because now the programmer has to maintain this next value. Okay. Okay. Another way that that functions are unsafe are these functions that always return a pointer to the same global variable. Or typically it's a static variable, but they always return the same value each time, the same address. Okay, so you can see this is similar to that race that we encountered before, where we were passing the address of a connected file descriptor to a worker thread. Okay, so now we're creating a race. So let's say one thread calls this function. So for example, ctime takes this time struct as an argument, okay, which it can correspond to an arbitrary time. It could be the current time or just some arbitrary time that the caller constructed. And it returns a pointer to a char star. So it returns a pointer to a string that represents the date and the time. Right? So an ASCII string that represents the date and time. But it's always returning a pointer to the same location in memory. Okay, so you can see the problem. If thread A calls this ctime function with one time struct, it gets back a pointer to the character string corresponding to that time struct. But now let's say before thread A can read that string, another thread calls ctime. And that instance of ctime will overwrite the copy of the time string for that thread A computed. So when thread A finally gets a chance to access that time string, it's accessing thread B's time string and not thread A's time string. Okay, and it just depends if thread A can get to that and read that variable before thread B overwrites it, then everything's fine. Otherwise, thread A is accessing the wrong time string. Okay, so there's a couple of ways to fix this. Like, we could rewrite the function, the ctime function, to take add another argument that passes in the location, the address of the time string. So we could require the caller to allocate space for the time string and pass in the address to the ctime function. Okay, but this would require us to change all the instances where we call ctime. But we'd also have to change the implementation of ctime in the libc in the library, right? And so we can't, we don't have access to libc source on our system, right? So that's just not a feasible thing. Plus, it would break every other program that called ctime, right? So we just can't do that. A better option is to create a new function of our own, okay, called ctime underscore ts for thread safe. So we'll create our own sort of wrapper function for the ctime. And we'll use a technique called lock and copy to provide thread safe access to ctime. So the way it works is that we'll write this new function, ctime underscore ts, which, just like ctime, takes this a pointer to this time struct, but then it adds a second argument, which is a pointer to the thread's private copy of the time string. Okay, so the caller allocates the space and passes the pointer to this to that string. And then within ctime, we have a local variable called the shared pointer. Okay, so this is going to point to that shared global data structure that ctime is accessing. And so first we do the lock, that's the lock part of lock and copy, by acquiring a mutex. And then we call ctime. So only one thread at a time will have this mutex. So whatever thread, so once we return from P, we know that we're the only thread in this critical section. So we call ctime, the normal libc ctime function, which returns a pointer to this same location. And then we do the copy part. We copy that string to the private string that was passed into our function. Once we've done the copy, then we can release the mutex, and then we return a pointer. We return private P back to the caller. Right? Okay, so, and we don't, this is just more of a convenience to the caller, because programs that are using ctime are expecting to get that pointer back. Okay, so by using lock and copy, we have to make changes. We have to write this new function, but it's fairly simple. And then we have to make changes every place in our program where we call ctime. We have to update those to calls to ctime underscore ts and create this local string array. Okay. Yes.
I'm a bit confused by why it has to be a pointer, or like why it's not just any type of variable that would cause this kind of condition, or why it's just a pointer that would cause it to right?
Well, typically these functions are returning pointers to some data structure, and so they're sort of updating the data structure and then returning a pointer to it. So it wouldn't make sense. I don't know how. I guess it could return a struct, and it would always return. No.
Okay, so these kind of things would never return an integer or.
I can't think of any reason why they would return anything but a pointer, because they're typically updating some data structure and then returning a pointer to it.
If they did in that case, then it would cause an issue possibly.
If they were returning, scalars, those scalars would always be returned in EAX or RAX, right? So actually, that would be okay, right? It would just be. It's the pointer that causes the problem, because it's always returning that value in EAX, but it's always returning the same value in EAX, always pointing to the same data structure. Okay, good. Okay, now one potentially significant disadvantage of lock and copy is that this copy might not always be as simple as just doing like a stir copy. If it's a complex, if if the function that you're calling is computing some complex data structure, like a nested, a struct which contains structs and pointers to arrays, then this copy can get quite complicated, right? It would require what we call a deep copy. So that can be very difficult too. But in this case, it's simple. We're just copying one string to another. Okay, and then finally, the fourth class of thread unsafe functions are functions that call unsafe functions, right? So it's kind of obvious. And then the obvious fix is to not call thread unsafe functions from within your function, and then you can make it thread safe. Now, there's a very interesting and important subclass of thread safe functions called reentrant functions. So a function is reentrant if it contains no accesses to shared variables. Okay, so if every variable that it accesses is contained is declared as a local variable and stored on the stack for that function. Okay, that's called a reentrant function. And because there's no accesses of any kind to shared variables, there's no synchronization required because every function is accessing its own local copy of all the variables. And if multiple threads execute two instances of a reentrant function, it's okay. Each thread has its own separate stack. So you don't need to worry about any kind of synchronization. They can run independently. So the reason reentrant functions are so important is because it's expensive to do synchronization. And so you can avoid it completely with these reentrant functions. So they're efficient. So as the diagram shows, every reentrant function is thread safe, but not every thread safe function is reentrant. So we saw that before, right? When we have a function that accesses a shared variable, we can make it thread safe by protecting it with a mutex. Okay, but it's not reentrant because it's accessing shared variables. Okay. Now, all the functions in the standard C library, which are enumerated in the back of your K&R text, are thread safe. Okay, but not necessarily reentrant. And most syscalls are thread safe with with a few exceptions that I've listed here. I don't think this is complete, but these are just sort of examples of some notable ones. And so for each of these thread unsafe functions, Linux provides a reentrant version, which is denoted by _r. And then that reentrant version has a different set of parameters, right, typically. The only exception that I know about is inet N2A, which is sort of an obsolete network protocol for converting sort of binary network addresses to human-readable ASCII addresses. But this has been obsoleted by other calls, so I guess they just never bothered to create a reentrant version for it because there's other options, alternatives to using that. Okay, another thing we have to worry about, as we've seen, is races. Okay, and this is the real bugaboo in threaded programs. And it typically involves some kind of unexpected sharing. So in this case, I want to revisit this incorrect threaded program where we introduce a race by passing, when we create the thread, we pass the argument to the thread, which is like the local thread ID. We pass an address of a variable that we have stored on the stack. In this case, the the loop iterator. And so we've seen that this causes a race. So we set initially I as 0, and then we create a new thread, which is pure thread 0. And then this thread dereferences the pointer to get its local copy of this sort of local thread ID. But now we've introduced a race between the increment of I and the dereferencing of the incrementing of I in the main thread and the dereferencing of I in the peer thread. So if this dereferencing happens before I is incremented, then we're good. But if this dereferencing happens after we increment I, so in other words, when I equal 1, then we get the wrong value in the peer thread for my ID. So you might wonder, I think there was a question before about, this seems, the odds of this happening seem so low. Why are we even worrying about it? So we actually, just to sort of test this out, we wrote a program to see if we could actually see this race in practice. And that's one of the great things about like 213 is that we can just try stuff out, right? So we just tried it out. So we wrote a simple main thread that creates 100 different threads, each with we pass as the argument we pass the address of this local variable I. Okay. And then in each peer thread we detach the thread, dereference, and then we have a function that saves the value. So we're storing that value of I for future reference. Okay, so now if there's no race, each of the 100 threads would get a separate, distinct thread ID, right? So each value 0 through 99, if we made a histogram of it, there would be exactly one instance of each value of I. Okay. But if there was a race, there would be, for some values of I, there would be multiple instances that were encountered in multiple threads. Okay, so you can see if we go back here, if the peer thread loses the race and I gets incremented before it can dereference, now we've got peer thread 0 actually gets an ID of 1. Okay. And then peer thread 1, if there's no race, it'll get the correct value of 1. So now we've got 2 instances of 1. Okay. So let's look. So this is the case. So we've plotted the results for a case where there's no race. So along the x-axis, sorry, this is too small. The x-axis gives us all the 100 values of I, 0 through 99. And then the y-axis is the count. So this is we're doing a histogram of for all the values 0 through 99. So in this case, every value has exactly one instance, so no race. There was no race no races involved in all 99 or all 100 instances. If we run it on a single core laptop, so now each thread is sort of taking its turn on a single core, it happens a few times, right? So there's a few times where the one thread gets preempted and the other thread begins to run before it can. So one thread gets preempted before it can dereference the variable, so it gets the wrong value. But it's not very common. It happened 1, 2, 3, 4, 5, 6, 7 times. But now if we run this program on a multi-core server, you can see it happens a lot. In fact, it happens most of the time. So we almost never get the correct value for my ID. Okay, so this is just another example of some of the things that can just drive you crazy if you're not careful when you program in threads with threads. Okay, and so as we saw, the way to eliminate these kind of erases is to avoid the sharing of state, and in this case by allocating for each thread allocating a separate block in the heap that'll hold the local ID for that thread, and then passing a pointer to that unique block of storage to the thread. Okay, so if all of that isn't enough to worry about, and by now you should be losing sleep at the very thought of writing a threaded program, another thing to worry about is deadlock. Okay. So here, a program is deadlocked if it's waiting for some condition to occur that will never occur. Okay. So let's say a typical scenario, right? P is a potential, the P operation is a potential problem because it blocks, right? And it's waiting for that semaphore that it's blocking on to become non-zero. Well, it's not too hard to imagine scenarios where there's some combination of P operations that sort of block each other out, okay, and make it impossible for the condition they're waiting on to occur. So, for example, let's say you've got two threads that need two threads, 1 and 2, that need two different resources, A and B, in order to proceed. So they have to do a P on the mutex that's associated with the mutexes that are associated with these two resources. So let's say process 1 acquires A. So it does a P on A's mutex. That's 1. It's okay. So it succeeds. So it acquires that resource. And then it gets preempted by thread 2, which acquires B first. Right? Instead of acquiring A, thread B, for some reason, acquires B. So now thread A holds the lock on resource A, and thread 2 holds the lock on resource B. And so now, let's say thread 2 gets preempted, and thread 1 runs, and so now it's waiting. It tries to acquire the lock on resource B, but thread 2 holds that lock. And at the same time, thread 2 tries to acquire the lock on resource A, but process 1 is holding that, right? So so here's a case where thread A is waiting for this semaphore associated with B to become non-zero. So it's blocked in this P operation, and at the same time, thread 2 is blocked in the P operation for resource A. Neither of those semaphores will ever be released, so thread 1 and 2 are deadlocked. Okay, and it happened because there was this innocuous little bug in this case where the threads acquired their resources in different orders. So here's an example of a program that deadlocks. And if you looked at this, the fact that it's wrong and buggy doesn't jump out at you, right? So this kind of stuff is very subtle. So here's a program. We're going to create two threads. We've got an array, and we have an array of mutexes, an array of two mutexes. And so we create two threads, and we pass each thread, it's a local thread ID, so of 0 and 1. And so here we're avoiding the race, we're just casting this thread ID to a pointer, okay, which is a little strange, but it's okay. And then we're waiting for those threads to finish. Okay. Each thread is going to acquire these two semaphores, these two mutexes, but it's going to do it in a different order. Okay, so it's going to do it as a function. It's going to take the ID. So thread 0 will first acquire mutex 0, and then acquire mutex 1 minus 0. So then it'll acquire mutex 1. And thread 1 will first acquire mutex 1, and then acquire mutex 0. Okay, so if we were to draw that and then it'll increment count. So this is totally bogus, but It's just to illustrate the problem. So you can see thread 0 does a P on semaphore 0 followed by a P on semaphore 1, and thread 1 does a P on semaphore 1 followed by a P on semaphore 0. And so we can see that this is a problem very clearly if we go back to our progress graphs. So if you look at thread 0, it's doing a P on semaphore 1 and a P on semaphore 1 followed by a V on semaphore 1. And thread 1 is doing a P on semaphore 1 followed by a V on semaphore 1. So if you take the intersection of these two regions, you get the forbidden region for semaphore 1. Okay, so this is the region that enforces mutual exclusion. So on the resource associated with semaphore 1. And if you do the same thing for semaphore 0, so here in thread 1, we're acquiring semaphore 0 here and releasing it here. And in thread 0, we're acquiring it here and releasing it here. So if you take the intersection of those two, you get this forbidden region for S0. Okay, now the problem is this region here, this so-called deadlock region. Because by the rules of, time can't go backwards, once a trajectory enters into this deadlock region, then it's doomed. Right? Because once it enters this deadlock region, there's nowhere for it to go. Eventually, no matter how it progresses, every trajectory will lead to this point here where it's boxed in and can no longer proceed. And interestingly, this region back here, on the sort of the tail end of these two forbidden regions, this represents states that can never be reached. So these are unreachable states, which may or may not be interesting. And then what makes this so nasty is that it's non-deterministic, right? Some programs, some trajectories, if they get lucky, they'll skirt this deadlock region, and then the program will run fine, right? Okay, so if a trajectory maybe just by some arbitrary scheduling decision made by the kernel, the trajectory gets past the deadlock region in this direction, and then it'll eventually run without any problem. So it's only if a trajectory lands it within the deadlock region then that we're in trouble. So this is the really nasty part, is that you may run your program for 1,000,000 times, and every trajectory, every one of those 1,000,000 trajectories skirts the deadlock region. Okay, but on the 1,000,001st time that you run it, it enters the deadlock region and then deadlocks. Okay, so it's a very tough problem to deal with. Now, fortunately, it's easy to avoid if threads that are acquiring locks on resources acquire all those locks in the same order. Okay, so in our example, if we rewrite this program so that each thread 0 and thread 1, acquire their locks in the same order. So semaphore 0 first, followed by semaphore 1. Then if that happens, and you can see it eliminates the potential deadlock region. Okay. So now any trajectory that we take will be fine because we've eliminated that that deadlock region. And the order that we release the locks doesn't matter because that sort of affects it affects this sort of unreachable region, you know, the size and shape of this unreachable region. But the order that we release the locks can never introduce a deadlock region. Okay, so that's it for today. Hope you all have a very nice Thanksgiving holiday, and we'll see you on Tuesday.